It's interesting to note that when I got into water science, I didn't really have any ambition to change anything in water science. I was mostly looking for a resolution to my little thing that deals with meteorology, just simply the notion that as you increase surface area, you increase surface tension. That was mostly what I was concerned about. But in the process of resolving that and coming to the realization that polarity does have that can be neutralized by hydrogen bonding, really strange little element to it, which without that, my theory wouldn't make sense. And it's because I was so focused on trying to make sense of my theory that I discovered this. Didn't really have any intention to discover it, and actually discovered it about 3 years ago, and then I kind of dismissed it at first. I kind of thought, oh, surely someone else has thought about this. I'm sure it's just a matter of just looking it up. And every once in a while I'd go look it up and I couldn't find it. No one else had thought of this. I eventually came to convince myself no one else had thought of this. But even then, I didn't really want to get involved with the water sciences. I wanted to just get confirmation that surface tension and surface area maximize, produces a plasma. That was my only concern. And so the science has to some degree become a religion. It's become its own entity in and of itself, and they just want to continue that. And unfortunately, that's just a normal part of being human. We all tend to look at things in terms of our beliefs, our collective beliefs, and we look at things that confirm what we all believe. We ignore anything that doesn't confirm what we all believe. But here's the things you're going to see over and over again. To them, polarity is a constant. It's nothing to even be debated. It's just the way it is. H2O is a polar molecule. It's that simple. Well, obviously, to me, it's not that simple, as I've explained. Ab initio. Ab initio is a fancy word for first principles. Ab initio just suggests that they are basing their understanding of what they're observing on the first principles associated with all chemicals. One problem with that: those first principles, ab initio, work perfectly for all chemicals except for one, and that's the H2O molecule. Actually, there might be others, but that's also because they're polar. Now, here's the thing. Those first principles are based on more normal types of bonds, specifically ionic bonds, because those are the kind that are closest to H2O, but aren't really H2O. Now, the thing about an ionic bond is it's just a linear bond. It's just a connection between two molecules. There's no variation associated with it. And so it kind of gets back to this first one here. If you start out assuming something is what it isn't, you're going to have problems. So one of the things you'll notice when you read these papers in water science is that you hear this term a lot, ab initio. It just means first principles. It also means they're hiding the fact from you that the first principles they are assuming have to do with something that has nothing to do with water. And here's another assumption that kind of feeds into that, and that's simply the notion, the common sense notion, that if you have more bonds, it should be more strong. Seems like it makes sense. It does not work with water, though, as we described. And here's the reason it doesn't work. With water, when you have only one bond, you still have some polarity, and that's where you get the rigidity. That's where you get the tensional forces. In liquid water, it neutralizes the polarity, so you don't have. So look, there's more bonds here, and there's less here. Yet this is a strong bond, and this is a weak bond. That's very confusing to people. People don't like it when you flip common sense on its head, but that's what water's doing to us. It's flipping common sense on its head, and it's saying less bonds is strong, more bonds is weak. Strange, I know, but that's water. And the fourth source of pathology, I guess you could say, in the water sciences, it's just this notion that ice is a lattice. It's really not a very sound notion. It's kind of a nonsense notion. it's an idealized notion. The actual gentlemen who introduced this notion were back in I think they wrote a paper in 1933. It was Bernal and Fowler. They were British, and they developed these models of ice, and they found different ways of fitting them together, and they looked kind of neat, and people just kind of fell for it. Unfortunately, like a lot of things in science, you have to be cognizant of the fact that people tend to have natural inclinations to fall into idealized notions, and this is one of them. Has to be some other underlying cause as to why, when water gets down to that temperature, it relatively suddenly, and not always, because there's super cool water, but relatively suddenly, it forms into ice. Well, that explanation is that there are bonds being broken, not that it is forming into a lattice. And that bonds being broken actually activates 1/2 of the polarity, allowing the solid form of water to emerge. Now, I understand that there's no clear way to conceptualize exactly how or why that happens, and why it happens at 0 degrees, and there's definitely a mystery there, and I've attempted to address it in my paper, but I don't think I fully captured what's going on there either. But it's important to understand something. Just because you have this idealized notion of a lattice doesn't mean it's true. It's just a notion. You don't have any direct evidence of it actually existing. Ice really couldn't exist unless there was polarity, and polarity is neutralized in the liquid state. So, and the only way to regain that polarity is by breaking some bonds, and so that has to be what's happening with ice. It doesn't have anything to do with the lattice. Another problem in water science is that if you ask them to explain why they believe certain things, they just simply won't have answers. They'll have excuses, and almost always those excuses will get down to, well, water has anomalies. Okay. So, nothing wrong with our theory. It's just that water is weird. It doesn't fit into our theory. Well, that's wrong. If water doesn't fit into your theory, that's because there's something wrong with your theory. And maybe that is the biggest clue here, is that it's really about a model, and it's about them protecting their model from scrutiny. A model that needs to be protected from scrutiny is not a good model, and that's what we're seeing in the water sciences too. They have a model they're protecting from scrutiny, and they're doing it by confusing people with stuff that doesn't really matter. You're going into all these details about all these other causes of that space that's in between molecules, when really the cause is understanding polarity. Once you understand polarity, the problem disappears. Also, once you understand that ice doesn't form into a lattice, that problem disappears. And all of the anomalies of water start being knocked off one by one by one. I'll give you a big one right now. The heat capacity of water. Well, the understanding that I developed resolves it. Because let's imagine this is a oxygen molecule, and let's imagine this is a hydrogen molecule. I'm saying that as the hydrogen bond is completed, as they come up and touch, their polarity drops to 0. Therefore, any kinetic energy that was associated with them coming together doesn't just instantly disappear, it's actually conserved. Because after they hit, there's a rebound effect, and they go away again, and that energy is stored, and then it comes back again, and that causes a rebound effect. So you have, within water, you have these billions or even trillions per drop of these little pendulums going on constantly, and these pendulums are the origin of water's ability to absorb a lot of energy. because this is the mechanism that allows this energy to exist without being quickly passed on, as is the case with most of other substances, let's say solids, for example, or even other liquids in which there is some kind of a hydrogen bond, is more of an ionic bond, I should say. And this is it. This is why water has this high heat capacity